Right, great, thank you. All right, everyone, welcome to our first virtual colloquium of the fall. It is my pleasure to introduce Gina Henderson. Gina is an associate professor at the U.S. Naval Academy in Maryland in the Oceanography department. Now, her work largely deals with the hydrologic cycle at high latitudes. So in many of her publication titles, you will often see the word snow in there. But she has also done a lot of extensive research with her colleague Brad Barrett, who's also joined us today, I saw, on how the MJO influences high latitude regions. So this is the work that that made me aware of her name. It's a lot of really excellent work and certainly related to what she will be speaking about today. So without any further ado, Gina, I'll let you go ahead and take over.
Thank you so much, Stephanie, and thank you to you and the department for having me and virtually. And again, I'm honored to be here for your first virtual colloquia series. So the title of my talk today is Intraseasonal Variability of High Latitude Climate. And I just want to take a moment, just make sure I'm on the right screen here. I just want to take a moment to thank my collaborators here. Stephanie mentioned that my good colleague and friend at the Academy, Dr. Brad Barrett, is joining today. I had him, I was informing him along the way of this talk just because I'm actually headed out on maternity leave in 2 weeks. So just in case anything happened on this talk, he was going to swoop in and cover for me, but thankfully he didn't have to do that. Also, we are working with Lieutenant Matt Lafleur, who is actually a former student of ours who has now made his way back to the Academy and working as a lieutenant. And he wrote to us last year wanting to resume research with us. So it's a great pleasure to work with him again on some of the latest work that I'll be presenting. He's been instrumental in that. So it's great working with him again, although it makes me feel old having a student who has left and now come back as a lieutenant. And then also some of the results that I'm going to highlight are two former students, Ashley Lois and Hadi Al-Sawi, also helped out. Also, I'd like to briefly mention this work has been funded largely by NSF, 2 grants. One was the earlier grant dealing with the Arctic portion, and then we have a current Antarctic grant. So I'd like to recognize and thank NSF for the support. So really, what precipitated this research we started it quite a while ago. Our first paper that I'll highlight, and apologies, it is a little old, but I promise I'm going to get to some newer stuff. It was published back in 2014, and what we were really looking for is we were really looking to answer the question, can the tropics explain our rapidly changing Arctic? And we've used this kind of cartoon to really to illustrate our hypothesis of basically our suggestion that MJO convection in the tropics can excite a poleward wave train that then will impact and project onto the Arctic atmosphere via insulation, precipitation, circulation features, and then that in turn atmosphere will affect surface conditions up in the high latitude regions, in this case Arctic sea ice and snow cover. So again, what I'm seeking to kind of convince you of, hopefully, and I know that there's a lot of MJO people in the audience, but then some of the people in the audience might not be as familiar with MJO. What we're really trying to affect such remote phenomena as Arctic sea ice or snow depth, and I'll definitely be focusing on the sea ice here for this talk, and then what do we mean by intraseasonal timescales and what is the MJO? So again, I'll briefly go into this. I realize there are many in the audience who know far more on the MJO than I do. But again, the MJO is here kind of illustrated by the seminal figure from Madden and Julian themselves in 1972. It's basically seen as an anomalous eastward moving convective cloud cluster. Again, 2,000 to 10,000 kilometers in horizontal scale, and again, it propagates. So it's most vigorous in the eastern hemisphere, and it comes with accompanying pressure and circulation perturbations. It also moves east, and circumnavigates the planet along the equator. So the main key features here is that it's got a periodicity of about 40 to 50 days, progresses eastward, and is generally stronger in the winter. That's obviously Northern Hemisphere winter, December, January, February, and spring, March, April, May, than in the Northern Hemisphere summer. And we actually did, with Lieutenant Lafleur, we did a RENA's paper a few years ago looking at the kind of a climatology of the MJO in various seasons. I'm not going to touch on that today, but I'd point people to that if they're interested. So obviously in this seminal figure here, it's just showing obviously the 8 different phases and that eastward propagation of that cloud, that convective cluster eastward, again around the equator. And then obviously here we kind of see a cross-section view, obviously with this cloud cluster, with obviously our kind of in, up, and out movement of the MJO. So some background and motivation. How did we get here? Well, there's lots of theoretical evidence for the extratropics responding to tropical forcing, going back, as far as 1981 here. So I'm going to just highlight a few of these kind of motivating papers, earlier papers. So Hoskins and Crowley in 1981. Again, if they injected kind of an upper tropospheric heating source in a 300 millibar height field, and again saw the resultant perturbations from this as a result of this tropical heating source. And again, we see this wavy response in response to this heating source. Building on this, Blade and Hartman in 1995 again looked at meridional wind's response to a heating dot. So again, here we see again a heating source, and again the meridional wind response as a result, and we can kind of see this alternating pattern and this wave-like pattern as a result. Gin and Hoskins in 1995 took it a little bit further, obviously, and we're looking at moving the heat source around, and again looking at the different responses, if the implications for spatially varying such heat source, and again varying results, but still this wavy atmosphere as a result of this upper tropospheric heating source. Matthews et al. In 2004 looked at 200 millibar wind differences and between opposing phases of MJO, and this kind of reminds me of a lot of the different, a couple of the different results I'll show today here, where we are looking at kind of compositing of different phases of MJO and how different phases of MJO can respond differently in terms of the atmospheric response. And then finally, a more recent paper, so in Sun in 2012, again, here showing kind of the upper level stream function anomalies for MJO heating over the Eastern Indian Ocean. And here they're showing not all of them, but the different wave number responses or stream responses as a result of that upper heating source in this location. So again, all of this kind of builds to, again, a certain amount of evidence in terms of MJO impacting the extratropical atmosphere. And again, a framework for how it does this can kind of be seen in these couple of figures here. So on the left from Moncrief in 2007. And again, just highlighting again the MJO and the slow, moist Kelvin-Rossby wave. And again, this idea of Rossby wave trains either extending into the northern hemisphere or into the southern hemisphere, as in terms of again how we're extending and how the MJO is projecting and influencing the extratropics. And then in terms of MJO scale, so if we kind of try and place MJO in context of some other atmospheric teleconnection patterns. Again, we can kind of see here, obviously MJO is definitely an intraseasonal mode of variability. So again, here we're talking about interacting on a seasonal cycle. Again, there have been plenty of papers that have looked at MJO and El Nino. And one of the big arguments that I think I've heard over the years is okay, well, isn't in the extratropics aren't the teleconnections of, say, the North Atlantic Oscillation or Arctic Oscillation more prevalent in terms of affecting and projecting onto extratropical atmosphere? Well, again, I would argue that MJO interacts with these other modes. So in perhaps a secondary way, the MJO is projecting onto the extratropics via some of these other teleconnections as well. And again, in terms of scale, just some examples of different scales can be seen here in some of these papers listed below: MJO and Precipitation by Barrett et al. In 2012, MJO and Air Quality, again by Barrett and Ragsdale in 2013, and then MJO and Other Weather Regimes by Farquhar in 2016. So how do we measure the MJO? Well, there's various indices that we can measure the MJO. One that we have used and is pretty much widely used within the community was developed. Obviously, I'm sure many of you have heard of the Wheeler and Hendon index. And what they used was the principal component analysis of 3 variables: the outgoing long wave radiation, zonal wind at 850 millibars, and then zonal wind at 200 millibars. And all of these variables were considered between 15 degrees south and 15 degrees north. Again, the index is called a real-time multivariate or RMM index. And the leading 2 principal components, the RMM1 and RMM2 forms of this phase space, form the MJO. So here we have RMM2 in the diagram on the right here, on the y-axis RMM1, and this is the classic RMM phase space diagram. And we can see here that our phases 1 through 8 are in a counterclockwise motion, going from the Western Hemisphere into the Indian Ocean, Maritime Continent, and Western Pacific. Again, for those who aren't familiar, we have a unit circle in the middle of this phase space diagram, and what we tend to do is we tend to consider any MJO occurrence with an MJO amplitude of less than 1, meaning the MJO is plotted inside this unit circle as being inactive, because again, at that amplitude, there's not really much difference in phase space between one phase and the other, whereas if we have an amplitude above 1, we are outside that unit circle, and there's a distinct difference if we were, say, in phase 1 versus, say, phase 4. So this index, again, allows us to assign a phase and intensity. Intensity, think of, again, how far we are away from the unit circle out in the phase space diagram. And again, the Wheeler and Hendon developed these 8 phases for the MJO. So this brings me on to the goal of the study, and the goal of kind of this talk and that I want to kind of is to identify and quantify the impact of the Madden-Julian Oscillation on high latitude regions. So specifically, the relationship between MJO and Arctic sea ice concentration, and the Southern Hemisphere atmospheric variability, and then also a sneak peek at some kind of our most recent work where we've started to look at Southern Hemisphere sea ice concentration. And so the remainder of this talk, I'd like to give examples of each of these above, but I am going to, as Stephanie mentioned in the introduction, we have done work on Northern Hemisphere snow and MJO, but for the purpose of this talk, I wanted to kind of stick with sea ice. So to focus on the relationship between the Madden-Julian Oscillation and Arctic sea ice concentration first, we go back to this schematic, and really what our hypothesis here started off with, this was our kind of first look back. We probably started this work back in 2013, I would say, again, the hypothesis is that Pacific convection or MJO excites a poleward wave train. This affects atmospheric variables in the Arctic, such as sea ice concentration, terrestrial snow extent and depth. And again, the goals here were to investigate the modulation of the Northern Hemisphere snow depth and sea ice by the MJO, and then also to connect any observed variability by examining patterns of mid-tropospheric circulation and surface air temperature. So the data we used for this project, again, we used the RMM MJO index, and it was obviously daily location or the phase and intensity of the tropical convection. And we considered an active MJO defined as one with an RMM of greater than 1. For this work, again, it's back a few years ago. We used we examined the reanalysis 2 and NCAR reanalysis 2 at 2.5 degree resolution. And again, this kind of dates this project a little bit. We considered this atmospheric data from 1979 to 2011. And we chose and started off with variables that we expected to be connected to snow cover and sea ice. So we started off with geopotential height at 500 millibars, and then also 2-meter surface temperature. And then the ice concentration data we used was the NOAA CDR available from NSIDC, and that had daily gridded values. At the time, it was from 87 to 2011, and now obviously it's up through current through 2020. We decided to focus on the Northern Hemisphere winter and Northern Hemisphere summer season. And the main reason we did this is the nature of sea ice concentration, is that we wanted to examine months where sea ice concentration was changing distinctly in one direction. So you can see obviously here in the blue our winter season, our Northern Hemisphere winter season. So November, December, January, where we have obviously ice growth, and then May, June, July, where we had generally ice decline. So our methodology for this is what we first did was basically we took the sea ice concentration data, and the first thing we did is we created atmospheric composites. And the first thing we did here is we basically, for the Arctic atmosphere, we took daily 500 millibar heights for each of the 8 phases, and we binned them by phase of MJO. And so here we're showing on the left-hand side, we're showing the winter season, November, December, January average, and on the right, May, June, July. And what we're showing here is anomalies by phase of the MJO. And again, this would be our first argument for MJO, evidence of MJO projecting onto the Arctic atmosphere. And the evidence we're arguing here is a distinct wavy pattern. We can see here alternating blue and red, positive and negative 500 millibar geopotential height anomalies. And again, the sign of the anomaly center flips every 3 to 4 phases. And here we have going from phase 1 to going to 4, and then in our second column, 5 to 8. I'll note that statistically significant anomalies are indicated by the hatching here. So you can see here that in most kind of centers of geopotential height anomalies, they are significant at the 95th percent level. If we look over here to the right, in May, June, and July, we still see evidence again of a wavy atmosphere, but it's lesser, it's weaker in nature, but we still do get statistically significant 500 millibar geopotential height anomalies. So that was kind of our first look at the atmosphere. So then what we did is, and there's a lot going on in this figure, so I'll take a moment and kind of explain what we did. So we did this thing for, I'll talk first about this last column here of this figure here, which is delta SIC, or change in daily sea ice concentration. So the first thing we realized is that when dealing with ice concentration is obviously ice concentration doesn't change a huge amount from day to day, because ice obviously there's a lot of memory associated within a season. So the first thing we wanted to do was to change our ice concentration data into a daily change variable. So literally we took our daily ice concentration, day 2 minus day 1, and that is our delta SIC variable going forward. The next thing what we were looking for is, so we have evidence obviously from the previous figure that of this wavy anomalous mid-tropospheric signal. We did that at a 3-month average. However, as soon as we started looking at surface features such as the delta SIC, 10-meter winds and 2-meter temperature, we realized that we'd have to go to monthly data or monthly time scale because again, anytime we averaged up over a season, signals were very noisy and got washed out. So what we did here is we took we created 8-panel plots like these and composited the various variables such as delta SIC, geopotential height, 2-meter temperature, and 10-meter winds. And what we were looking for is areas of coherent ice change, and then we were looking to see how the atmosphere supported or not, in which case those ice concentration changes. So here, what I'm showing here is an example for January, and the top row here is for phase 4 January. And so we've got January sea level pressure, 2-meter temperature, obviously anomalous sea level pressure, anomalous 2-meter temperature. For the winds, what we have here is we have a combination of wind vectors, which are the actual winds at 10 meters, and in the vectors, the U and V winds. And then the shading represents anomalous V component winds. So obviously blue here is anomalously negative V winds, which would be blowing towards the south, whereas reds are anomalous V winds blowing towards the north. And then finally, our last column is showing anomalous delta SIC, or anomalous daily sea ice concentration changes, with blue values here indicating ice decline, and red values here indicating ice growth. So what we were looking for here is areas of coherent ice change. So if I look here at the top row, you can see here that all along the eastern edge of Greenland, we have a blue area, or an area of daily ice decline in January under MJO phase 4. And if we see how the winds correspond to this, so we have an area of ice decline under phase 4, and this is coincident with anomalous negative V winds. So again, you can think of southward moving winds, or V winds, that is kind of our hypothesis was that these winds are helping to basically blow ice away from the ice marge along the East Greenland coast, and again helping to contribute to this coherent region of ice decline. We also saw, if we look at 2-meter temperature, we have lower than normal temperatures associated with that southward flowing wind, which makes sense. And if wind is being advected from further north. And then we have anomalous negative sea level pressure. So then if we can bring your attention to the second row here, the second row is all MJO phase 7 for January. And what hopefully you agree with is that we see that basically the signal flips in pretty much all of the different fields. So where we had negative sea level pressure before, we now have positive sea level pressure. The same hatching indicates statistical significance at the 95th percent level. Where we had negative temperature anomalies, we now have positive temperature anomalies. Where we had negative V wind anomalies, now we have positive V wind anomalies. And indeed, we have a flipped signal in our sea ice concentration daily change. So now we're seeing ice growth. And I would say that ice growth, as we have kind of made these winds helping to kind of pile this up or accumulate this ice along the ice margin. So this was an example
it looks like John has a question.
Yeah, Gina, the winds appear to be highly ageostrophic along the coast of Greenland. Is that just the way I'm interpreting this 10-meter wind in the MJO phase 4 with respect to the sea level pressure gradient, or is there something I'm missing?
So in terms of the anomalous V winds, or the wind vectors themselves?
Anomalous V. It seems to me you have really strong equatorward flow along the east coast of Greenland. Is that because of the orography of the ice on the coast?
That's a great question, and I would say that again, in terms of is it a factor of the ice growth, I'm not sure. I'd have to think about that.
Okay.
But again, it's again obviously very coincident with that ice margin and with the coast itself. But
thank you.
okay. So if we move on to another example, so this area in January was focused on the North Atlantic region of the Arctic. Another example here, looking at this time the North Pacific, and the setup is the same in terms of the layout of the diagram. We've got sea level pressure, 2-meter temperature, 10-meter winds, and daily change in sea ice constant. This time, however, we're focusing on the Pacific sector, and we chose here phase 2 versus phase 6. And again, what we see here, if we start with the ice, with the sea ice concentration anomalies, we have kind of again it's a noisy signal, but more kind of ice growth in the reds colors, and again ice growth. So ice growth versus in the opposing phase we had ice decline, and again we have the flipping of the signal of the 10-meter winds, going from obviously negative anomalies to positive anomalies, from phase 2 to phase 6, negative temperature anomalies to positive temperature anomalies from phase 2 to phase 6, and then negative sea level pressure to positive sea level pressure from phase 2 to phase 6. So just in the interest of time, so in summary, what we had here from the MJO and Arctic sea ice is our conclusions from this initial study was that MJO does project onto the Arctic atmosphere, and this was evident from the statistically significant wavy patterns and the kind of consistent anomaly sign changes when we looked at the 3-month composite anomalies. And then also, when we considered MJO modulation of Arctic sea ice in winter and summer, we saw that regions of greatest variability shifting with the migration of ice margins and poleward and equatorward during the summer and winter. And I showed a couple of those examples in the North Atlantic and North Pacific for January. So what I want to move on now to is to look at the Southern Hemisphere. And the one thing that I'll say is that when we attacked this problem, there was a lot more work having been completed already on the Arctic. When we started looking at the Southern Hemisphere atmospheric variability and the Madden-Julian Oscillation, the amount of literature on the Southern Hemisphere was much less, and especially in terms of lags, as in at what lag does the Southern Hemisphere atmosphere lag tropical convection. So that's where we really started with this first project. We looked at, the setup was very similar, so I'm not going to spend too much time here. We used the real-time multivariate index again. We used NCAR reanalysis. And this time, however, our goal here was to examine height anomalies along the annular latitudinal band around Antarctica. And why we chose these latitude bands that are indicated here is, the diagram here is just showing the geopotential height standard deviation. You can see here that we chose the latitude band that had the greatest standard deviation. However, we also wanted to see how sensitive the Antarctic atmosphere was to the choice of this band. So we actually, throughout this work, we varied the band from 4 different bands to see how sensitive it was. But the greatest variability in height field was, again, between the 50 and 65 south, 50 and 65 degree south band, as indicated by the dashed circles here. So what we did here was we were trying to answer at what time lags does the Antarctic atmosphere exhibit the greatest response to tropical convection. In the Arctic, most papers that we read about and the lag that we typically used in the Arctic atmosphere was 7 days, but there was no such consensus for the Antarctic atmosphere. So to assess temporal lags between the MJO and the Antarctic atmosphere, what we did was a series of standard absolute anomalies for the latitude band, for 50 to 65 degrees south, where we basically calculated positive and negative standard anomalies in 500 millibar geopotential height. And so this is what we're showing here on the right-hand side. We're showing for the 8 phases, so phase 1 up here in the upper left, to phase 4 in the first column, and then phase 5 to phase 8. And each, now on the x-axis, we have the lag, starting with a 0 lag. So obviously the Antarctic atmosphere on the same day as the occurrence of MJO, of phase 2 in this case, if I'm pointing to this one. And then we lagged it out to 30 days. We tallied up and basically summed up the standard absolute anomalies for both positive and negative. And the 2 bars here are showing, the lighter colored bar is showing the total standard absolute error, and the darker red or darker blue is showing the statistically significant one. And what we can see here is that we can see here in different phases we have different peaks of standard absolute anomalies, and they occur again at different lags for different phases. Some phases here, such for example in phase 2, has it early on in the kind of phases 3 to 5 category, whereas phase 3 here is showing 2 negative peaks early on, and then obviously later out in the lag. So again, these lags varied by phase in the Antarctic atmosphere, and this I'm showing the results for June. So obviously the Antarctic, in the middle of the Antarctic winter here. So if we consider the June is still on the right-hand side, if we consider summer on the left-hand side, we did the same thing. And again, what we saw in summertime as well is that we saw, again, these lags, the lag of kind of peak geopotential height in positive or negative, really, again, it varied by phase and it varied by season. And just to point out, the M number here in the upper left of each phase number is basically just showing the number of occurrences that went into each of those composites. What we did, so this was all based on the 50 to 65 50 to 65 degrees south band. However, I will say that we looked at all of those 4 different bands that I mentioned at the beginning, and we also looked at varying not only at 500 millibar heights, which is what these plots are showing, but we also looked at both 300 and 700 millibars as well, because we wanted to see how it varied by different at different levels within the troposphere. Another way we looked at this to kind of look at things over spatially and over different phase space is we looked at geopotential height anomalies. So here is our 500 millibar geopotential height anomalies for 0 to 30 days. So 0 to 30 days on this Hub-Muller diagram is on the y-axis, whereas our x-axis with longitude. And what we're showing here is, again, height anomalies in the 50 to 65 degrees south latitudinal band organizes, and we saw that organized band responses with wave numbers 3 or 4. And what we saw here was that in some phases we had height progressions eastward after MJO convection that did progress eastward. So, for example, in phase 1, 2, and 3 here, we can see this eastward propagation of either negative or positive height anomalies, as opposed to other phases, such here showing here in phases 6, 7, and 8. Height anomalies kind of exhibited a more blocking or standing wave pattern, and again, not much eastward progression. So another way we can look at this in kind of a terms of spatially is if we look at phase 7 here. So phase 7 was a good example, kind of a not that much eastward progression, this kind of blocking or standing pattern. And if we can look at this in a different way. So this is that same phase 7, and this is that same phase 7, 500 millibar height anomalies. And this time, each of these panels, these 8 panels, is showing that phase 7, 500 millibar anomalies at day 0, day 4, day 8, so at 4-day intervals. And again, what we see here is that positive heights are the reds. Again, this was the Hofmüller diagram. What we can see here is that, again, the positive heights up to 20 days after MJO convection in the Western Pacific Ocean, and then the positive anomalies slowly move towards to near 120 west by day 24, and then weaken by day 28. So again, just showing kind of that persistent anomaly slowly moving towards that 120 west, and then finally weakening once we get out 30 days. So in summary, for a first look at connections with MJO and the Antarctic atmosphere, we found that MJO convection affects the southern hemisphere atmosphere around Antarctica, and we had the greatest response exhibit temporal lags between 3 and 25 days, and it was really dependent on the month. We looked specifically at June versus December, and then also by phase as well. Different phases were associated with different modulations. As I mentioned before, I didn't show much of this, but even despite different lags, the response was fairly even in different vertical levels. We compared 700, 500, and 300 for different swaths, and the responses were pretty consistent. Some MJO phases excited 500 millibar height responses that kind of resembled progressive waves, versus others excited 500 millibars that resembled more blocking or standing waves, for the example I just showed. So in the last kind of 5 minutes or so, I'm cognizant I want to leave time for questions. I wanted to talk about some new work that we've been doing. So after looking at the Antarctic atmosphere, we were eager to start looking at sea ice concentration. And this is that we've been doing this summer, myself, Brad, and Matt Lafleur. And what we, again, were looking at here, we were using the MJO RMM index again. This time we've moved on to using the ERA5 reanalysis data. So this work spans from 1988 to 2019. Obviously, the ERA5 is available at much higher resolution than the NCAR that we were using previously. But we initially started looking at 10-meter winds again, and 2-meter surface temperature, and also the same sea ice concentration data. So we started off by, I'm going to show an example from July sea ice concentration. And what we did here was we used a sector approach, and this was based on some work we had a student doing last year based on a paper that we were looking at how sea ice concentration changes by sector. So our 5 sectors we're kind of considering was the Weddell Sea, the Indian Ocean, Western Pacific, the Ross Sea, and the Bellinghausen and Amundsen Sea. And I'll just bring your attention, because I think the example I'm going to show, it really focuses on here the Weddell Sea and the Bellinghausen and Amundsen Sea. And what we did here is, again, I'll get these stars out of here in just a minute. But what this diagram is showing is it's showing July 7-day lagged daily change in sea ice concentration, like we used before. So that daily sea ice concentration is binned by phase of MJO and then tested for statistical significance. So we're only showing in the reds and blues here, and the reds we're showing positive daily change. In the blues we're showing negative daily change, and on top of the statistics that are only statistically significant. And then on top of that, we wanted to make sure that any occurrence that we're showing had at least 5-day minimum threshold, so that was also applied. So what I want to focus here on is an example from phase 2. in the Weddell Sea here, the Red Star sector, and the Bellinghausen and Amundsen Sea sector in the purple sector here. What we can see here is that we can see here a coherent region along the ice margin of positive daily change in the Weddell Sea versus negative daily change in the Bellinghausen and Amundsen Sea. So what we did here was initially we were saying, okay, well, what does the atmosphere look like? And how is the atmosphere potentially supporting these daily ice anomaly changes? So here, what we're showing again is our our 7-day lagged U and V winds, shown in the actual vectors, and then our anomalous V component winds. And what we see here is that we've got this nice kind of alternating or dipole of positive V winds in the red here in the Weddell Sea sector, and those positive winds would coincide with that, if I flick back, with positive daily ice change, whereas we have negative winds here. So negative V winds obviously would be going towards the ice sheet itself, and corresponding with some of that negative daily change. If we consider temperature, 2-meter temperature, we again see negative temperature anomalies coincident with positive daily change in sea ice concentration, and then positive 2-meter temperature down here in the red. So again, kind of just putting together our initial again hypothesis of stringing this together. So for the Weddell Sea example here, we saw positive ice concentration, positive daily change in ice concentration associated with positive anomalous U winds, which would be winds off the ice sheet, which is also coincident with negative temperature anomalies. So again, what we're still working on is to trying to tease out again the ice signal. It's pretty noisy, and we want to make sure that it's actually there, and we're doing it due justice. But that's been the challenge so far. So obviously the next step is to look at. We've also considered different lags. So we started out looking at 7 and 10-day lags, and so I was just showing an example of 7-day lags here, and also obviously for different months here. What we're finding here is again the different months play a big role in comparison to the Arctic paper and approach. So just in summary, what I set out to kind of give you an overview of the work that we've done is the goal was really to identify and quantify impacts of the Madden-Julian Oscillation on high latitude regions, and we have again looked at specifically at MJO and Arctic sea ice concentration in the northern hemisphere. Northern hemisphere snow I didn't show, and then southern hemisphere atmospheric work, and then also sea ice concentration. And with that, I think I'm just up around 4:15 for you guys, 5:15 for me. So I wanted to leave time for questions.
All right, thank you so much, Gina. That was very interesting. I will go ahead and open up the floor. First, do we have any questions from students? Okay. If not, and you're of course still welcome to either type it in the chat or say it out loud if you would like. Otherwise, I will go ahead and open up to the questions for anyone. I have a question person. Oh, there we go. John has a question. I have a question as well. I'll let you go ahead and go first, John.
Oh, you can, Steph. You can go first.
Okay. Thanks. So one of the things that I noticed is that for both the Arctic and the Antarctic, that you would have an increase in sea ice associated with warming, and then vice versa, where you would see cooling temperatures with less sea ice. So I was wondering, Do you think, since the MJO is a propagating pattern, do you think that the warming during one phase is in part responsible for the sea ice decline during the next phase, and vice versa?
So that's an interesting question. So I think that initially especially in the Arctic, what we were more concerned with in terms of trying to explain the ice growth versus, or the positive ice change versus negative ice change, we were looking more physically at potentially the impact of the winds with impacting the ice, like blowing the ice itself in terms of like piling up the ice along the ice margin, or encouraging it to obviously to break apart. So I think that's how we rationaled, especially in the Arctic, ice decline and ice growth with winds. In terms of 2-meter temperature, it seems a little counterintuitive with ice growth associated with anomalous positive temperature. However, I think what we were more concerned with there, or more interested to kind of point out, was that the atmospheric signal in terms of the temperature anomaly was, first of all, it was a coherent temperature anomaly under one occurrence, and then the alternating occurrence or phase that we were showing, it flipped entirely. So it was really indicative of a different atmospheric setup, or at least a surface feature. So again, perhaps I think your point about the temperature potentially affecting the next phase is a good one, but not one that we've actually considered much at all. But we were more focused on the physical aspect of the impact of the wind in terms of the ice margin. And then, as I said, in terms of temperature, just the fact that we had a coherent anomaly that flipped one way or the other, going from our one phase that we were highlighting to the other, if that makes sense.
Yeah, thank you. John, you can go ahead.
Thank you, Steph. Yeah, Gina, thanks for a great presentation. Very, very interesting stuff. And I'll admit at the top here that I don't know very much about any of this stuff. I'm trying to learn it as I go, but I am curious about two things, if I could ask. One is, there's all this in the presentation and in the literature, there's so much reference to the tropical heating source forcing Rossby waves toward the pole, as if that's the only direction they could go and that they won't run into any roadblocks on the way. And I've always had this notion in my mind that it depend to an extent where they go, that is, depends on an extent to what the waveguide in the middle latitudes is telling it to do. Because if you've got a strong jet that maybe is extended, let's say in the Pacific, does that not alter the direction of Rossby wave propagation? And if it's retracted and pushed well back to the west, that might open up a highway to the pole in the Pacific sector and so on. Or am I thinking about that wrong?
So I think your point is very valid, and I will also claim that I am, in terms of the dynamics here, and there are other people that I know are on this talk that are far more well versed in the dynamics of the Rossby wave propagation. It kind of goes back to, I would say, I think that your point is very valid, and it goes back to something that I mentioned early on when I was talking about the motivation, is that I would say that the MJO signal is noisy, and it's, in terms of how it propagates, through the extratropics, through the mid-latitudes up to the Arctic. Again, it's going to interact with the atmosphere, obviously. And this is where sometimes the argument here I've heard is, well, in terms of maybe especially Northern Hemisphere snow or Northern Hemisphere sea ice, there's so much literature that points to other modes of variability, such as the Arctic Oscillation and the Arctic Oscillation or the North Atlantic Oscillation. Well, my argument would be kind of along the lines of your point, that again, the MJO and the tropical variability is again going to propagate onto and affect these other modes, and then these other modes will affect these high latitude features. So I would argue that, in a sense, that is still evidence of MJO or tropical intraseasonal variability impacting high latitudes, but again, not necessarily in a direct way. Again, it's so I think your point is very valid.
Well, that's a really interesting perspective, and it makes me wonder, and I don't know if this has been done yet or not, perhaps you don't either. Has the Hoskins and Caroli idealized work been done with varying jets in the Pacific and Atlantic basins, and to see if there's different ray tracings that come in different, large scale scenarios in the mid latitudes? Because I think you're right. It's a mix of a bunch of different things.
But that's I mean, it's a very interesting idea for sure.
Thank you.
Okay, so first I will address, we have a question in the chat from one of our graduate students. Neil would like to know, how long does it take for warm temperatures and or equator whirlwind to reduce sea ice concentration?
So that's a tough one. So I would say that typically we have found, and the literature points to, a lag of 7 days for an MJO signal to propagate into the Arctic atmosphere. So then you're talking about the Arctic atmosphere then has to project onto obviously the surface feature. The nature of Arctic sea ice is very different than Antarctic sea ice in terms of, obviously in the Arctic we have multi-year sea ice. So again, I would say that it's not going to be, it's going to take a while. And I think that's one of the main reasons why we always went, when we started this work, we never dealt with the raw sea ice data, raw sea ice concentration. We always looked at the daily change. And by using and creating that daily change value, we're never saying that MJO is deciding Arctic sea ice. We're saying that MJO can affect where Arctic sea ice is changing. And that's really around the ice margins. So we are using a daily change value. So again, it can change day to day. So I would say, so that's kind of a long way of saying that it has to be longer than 7 days for sure. But even at that, we're talking about MJO really affecting ice margin, the marginal ice zone. Now, for the Antarctic sea ice, for Antarctic sea ice concentration, things are different. And I think that's why potentially it's been harder to tease out the signal, because the nature of Antarctic sea ice is that it's thinner. It has a very different seasonal cycle, as in it melts nearly completely and then refreezes and grows back within a seasonal cycle. So again, I think perhaps maybe some of the challenge that we're finding with the Antarctic sea ice concentration value is that potentially some of the interaction maybe and some of the ice response is maybe happening quicker because of that. But again, I would say that we need to, I'm not in a position to say that for sure yet.
Thank you. So Liz, you have a question?
Sure, thanks. That was really cool. Thank you for the talk. So this question is a little bit out of left field, and I'm hoping that you're more informed about these than I do and have some idea. So something that's I know puzzled a lot of people, and that's always kind of intrigued me, is that in coupled model projections of the historic period and the future, you see this big decline in Antarctic sea ice that doesn't match what was observed at all. Antarctic sea ice, for the most part, has stayed relatively constant up until like about 2016. And I know that folks have started to look in coupled models to see if some tropical teleconnections, so things like on interannual, interdecadal timescales, if there's connections between biases and those modes of variability and the Antarctic are connected. But I was wondering if you're familiar with if there's been any work done trying to connect things on these shorter timescales, intraseasonal and the MJO, to see if coupled models that do particularly poorly with the MJO or other modes of tropical variability are also ones that are particularly bad at capturing trends in Antarctic sea ice, particularly in places like the Amundsen Sea, since that seems to be a particularly troublesome location.
That's a great question, and I would say I don't have, unfortunately, I don't have a great answer for you. In terms of the ice response in these models, again, I'm more familiar, I'm more familiar with looking at kind of ice forecasts for the Arctic than the Antarctic. Because again, I have to say that my knowledge of Antarctic, of dealing with kind of Antarctic sea ice concentration is very much still in its infancy. I know that typically the models have struggled with MJO representation up until the so I'm most familiar with the NCAR CESM suite. And I know that typically up until this very latest CESM version, the models have really struggled to produce an MJO at all. So this one is the latest one. They are showing much better signal. And this has largely been just due to the model's failings to capture tropical convection in an adequate way to be able to just represent an MJO at all. So again, I think that right now MJO in these models is not necessarily how good it is. It's like, can we get it? I think versus so then. I think it's because with the latest version and we are now seeing a better MJO representation, I think that to try and then draw a comparison saying, okay, well now, is this the reason that maybe some of these models have performed poorly in terms of ice representation? I think that's a little too soon to try and draw comparisons there, but I think it's a really interesting idea. I think one thing that we found early on is that it's very challenging, I think, to look and consider Antarctic sea ice in a pan-Antarctic setting. And that's why we really quickly started focusing on a sector approach, because honestly, although there hasn't been the precipitous decline in Antarctic sea ice, it does vary regionally, and there's been interesting ways in which it's varied regionally in the last 5 and 10 years when we start considering a regional approach. So I think that's, as you mentioned, like the Amundsen Sea, I think that any efforts really needs to really focus on a more regional and sector approach rather than looking just pan Antarctic, because I think you quickly kind of get lost a little bit there. So great question, but I think my guess would be that we're not quite there to try and draw that conclusion, but I think it might be a very interesting one once the models are there and are capable of producing the various components need to try and answer that question.
Thanks.
We have one more question in the chat from one of our graduate students, Dave. He has, it looks like a two-part question. Does the Antarctic sea ice extent reach lower latitudes than Arctic? And also, could MJO signals or connections more easily affect Antarctic sea ice because of this, since that could be closer to the mid-latitude storm tracks?
So, sorry, the first question was, does Antarctic sea ice extend to lower latitudes than Arctic sea ice? Well, again, I would the exact latitude I would have to think about. But I mean, the inherent difference, obviously, between Arctic and Antarctic sea ice is that, again, the Arctic sea ice is largely bounded, obviously, by landmass. Now, we do have, obviously, Arctic sea ice extent in the North Pacific and North Atlantic sectors there, as I was kind of showing in Greenland, etc., along the east coast of Greenland, etc. Again, the actual latitude, I'd have to go back and look at some figures. But again, I would say, again, then the geography of the Antarctic sea ice is obviously that, again, it's not bounded by land. Obviously, we have Antarctic sea ice growing out from the land, but then obviously extending into the Southern Ocean. So the physical nature of both are very, very different. But I would say the big difference is the seasonal cycle is in the Antarctic sea ice is much thinner, melts away pretty much entirely throughout the winter season, and then, or throughout the summer season, and then regrows. So again, you don't get the multi-year ice that in the Antarctic sea ice that you get in the Arctic sea ice. Stephanie, would you mind repeating the second half of the question?
Yes, so the second part is, could MJO signals or teleconnections more easily affect Antarctic sea ice since, because of this, since that could be closer to the mid-latitude storm tracks?
So again, the exact latitude escapes me, but that's a great question, and I think it's one that I think I kind of hinted at, that I mean, I don't know, and I think it's an interesting one, one that I kind of hinted at when I was talking about our difficulty or the challenge of isolating a coherent Antarctic daily sea ice concentration change. That it's a noisy pattern, and I think it's a noisy pattern because again, we're talking about thinner ice that changes more dynamically maybe than Arctic sea ice. So again, the point of maybe the ice extending further to the north and therefore closer to mid-latitude storm tracks is a very interesting one. And I'd say, again, I would say that both potentially the northward extension, but also the thinner nature of the ice and the more variable nature of the ice might be also related to that as well.
Thank you, Gina. Does anybody else have any other questions? Okay, great. Well, thank you so much, Gina. That was a wonderful presentation and a lot of great work. And thank you so much again for coming out to, or not coming out, rather, logging in, I guess, to share your work. So thank you so much again, and we will see you later.
Thank you so much. And also, if anyone wants to reach out, please feel free to contact us, contact me offline if you have any follow-up questions. So,
thank you.
Have a great afternoon and good luck with the online 2 weeks.
Thank you.